All right, let's see if anyone shows up. So far, zero. That's a. I mean, yeah. Okay, so it's 11 o'clock right now, and there's no one here. Oh, there's 5 people here. Okay, so that's good. Um, so I'll start in a couple of minutes just to let people trickle in, since I gave kind of last minute uh, an email last night. So give people just a few minutes. Long time no see for everyone who's here, though. It's been what? This is the 3rd week now. Last week was spring break. The week before that was another snowstorm. So I hope everyone's doing well. I know you still haven't gotten your tests back, and we'll do that next week in class. I'm assuming there will not be another snowstorm, so we'll give back the test next week. Or I guess we can do office hours. If you come by on Friday, I can give you the test as well at that point. Because you still have to do factorial ANOVA before the exam, right? So we should be meeting next week, and the exam's the week after that. Is that right? I can double check. I have my phone. I'm just letting people trickle in for another minute while I check the syllabus. Right, so we'll meet next week, and then we'll do factorial ANOVA, right? So that's good. And then after that is when there's the exam. So I will see you at least once between the exams. Isn't that great? Okay. So 8 people here. That's awesome. So if you have questions, please do put them in the live chat, or email me, and I'll check that periodically. So we're going to cover 3 things today. One is correlation. So that was from the canceled recitation before spring break. Right, so we'll do correlation. We'll do that first because things that we'll do for today's recitation kind of build off of that. So there's correlation, so we'll spend some time doing that. And then we'll do paired samples t-test. Which you'll see is very familiar, right? I know you had a lecture on it. So you'll see it's very familiar to what you already know. It's just a small adjustment. So I think that will be, we can spend some time on that. And then we'll start going into really brand new territory, one-way ANOVA, or an analysis of variance. And we'll do ANOVA today, and we'll also do ANOVA next week in real recitation, and that will be on the exam. So the things that are on the exam in 2 weeks: correlation, paired samples t-tests, one-way ANOVA, and then factorial ANOVA, which is just an extension of what we'll do today. Okay, cool. So I want to do this kind of like a regular recitation. So I'll spend a few minutes talking about correlation, and then I'll give you a question, and then I'll let you guys work on it in real time, and then we'll go over it and then move on. I do know that this morning Dr. Kiliansky put questions and their answers for the canceled recitations on Sakai just this morning. So to really get the most out of practicing and doing recitation work, don't look at those right now. And I'll give you those questions, and you should work on them to their completion before you look at any answers. Just because they're there doesn't mean you should look at the answers, so we can do that afterwards. And if you don't want to look at them at all, we can go over them kind of quickly at the beginning of next recitation, if you prefer. I have no problem doing that. It's important to kind of get the practice in. Okay, so correlation, right? What is correlation? Well, so far we've been looking at predictors and outcomes, right? We've been looking at if sex or gender predicts height, right? Or we've been looking at things like does drug dose predict level of anxiety, things like that. Correlation is typically looking at two different variables against each other, and if they correlate, right? If they vary together. So correlation has to do with the variation that exists with both variables. So as the standard deviation increases for one, you see an increase in the standard deviation of another, is kind of how you think about it. So what are things that can be correlated? Let's say we want to look at, let's see if I can, if we look at like height and speed, right? So a question that we'll do is related to this. So let's say we have a bunch of people who vary in height and they also vary in speed. So we might get a point here. So this person is rather short and also rather slow. This person is tall but kind of slow as well. And so each point here is an individual where you're taking two measurements. You're measuring their height and you're measuring their speed. And from that, you get a bunch of different little points. So we have each person has a measure of height and a measure of speed. And what we do is we look at how they vary with each other, and eventually we'll see that there is a trend that exists with them that is called a trend line, and we'll talk about that when we get into regression. And the closer these points are to each other, this will go up. So this trend line will get, never mind, I'm jumping ahead. What we'll see here, correlation, is measured by this thing called R, or Pearson's R. So when you're calculating a correlation, you're solving for R. R is your kind of measure of interest. And the way you calculate that is like this. So it's the sum of Zx times Zy divided by number of pairs. So remember, your observations come in pairs, right? So you have a measure of height and a measure of speed. That's one pair. Another measure of height, another measure of speed. That's another pair. It's also the number of unique participants, right? So if you have 20 participants, you're going to have 20 pairs of observations. So it's technically called number of pairs. So if you think back to kind of the first test that we did, the first statistical test that we did, it was the Z-test, right? And you had to calculate Z-scores. So that's where these Z's come from. So what is a Z-score? I'll just remind you. It's X, which is your observation. So like if your height is 6 feet, your X is 6 feet, minus the mean. So if the mean of height is 5'11", this is 6 minus 5'11", divided by the standard deviation. So here, remember what you're doing, and this should all be a review, right? This is what we did before the first exam. So what you're doing is you're taking your observation and you're finding the mean, you're finding the difference, not the mean difference, you're finding the actual difference from your point to the mean, and then dividing it by the standard deviation. So you're putting that distance from the mean into terms of standard deviation, and that's what z is. And then you use z in your equation for r to calculate the correlation. So when I said before that the correlation is measuring how two variables co-vary, it's looking at how measurements of standard deviation in one relate to the measures of standard deviation in another. So x and y. So that's what we're doing here. So the first question that we'll do is question number 2. And I'm going to put some given data up here. And I'll also give you these equations again too, so don't worry if you didn't copy them down. Okay, so correlation. So this is it's chapter 11 in the old book. Chapter 9 in the new book. And that corresponds to page 324 in the old book and 296 in the new book. We'll do number 2. And I'm going to give you the z-scores, because we also have to cover 2 other topics. So this question is looking at if height and speed are correlated with each other. So we have height, and we have speed, and then we have the z for height and the z for speed. So here we have, these are the raw scores in inches. Those are the raw scores in inches, and then here are the z-scores. Now, even if I didn't give these to you, you should know how to calculate these, right? Whoops, that's 8-1. It's that you would have to find the mean and standard deviation for height, and then you would take each score, so like 60, 55, 56, etc., subtract that from the mean, and divide it by the standard deviation. Oh, it's not negative. I was like, how is 0.52 both negative and not negative? That's because it isn't. Okay, so those are your scores for height, and then your scores for speed. Again, those are the raw scores, and then the z-scores are definitely slower using this pad than using the board. That's okay. Okay, so that's all the raw data. That's the data you can expect to get. And remember that R equals Zx times Zy, the sum of this. Sorry, I'll erase that. R equals the sum of zx times zy divided by number of pairs of observations. Jenna asks, will we have to calculate these z-scores on an exam? Obviously we know how, but just asking due to the time it may take. So you definitely won't have to calculate the means and standard deviations. I haven't seen the exam, so I don't know for sure if you'd have to calculate the z's. I'm fairly sure that they'd be given to you, that the actual z-scores would be given to you. But you, at least I can say you'd be given the mean and standard deviation, so at the very least you might just have to do some subtraction and quick division to find z's, but I would be fairly certain that they'd be given to you. Okay, so, and one other equation, whoops. You need degrees of freedom, right? And degrees of freedom for R is number of pairs minus 2. So it's the same as everything we've been doing, right? You're going to find your test statistic, in this case it's R, and then you're going to find your degrees of freedom. Then you have to find some critical value for R in the back of the book using the R table. And then you compare your R to the critical value of R and make some decision about a null hypothesis. So think about what the question is asking. So in this case, is height correlated with speed? And then you want to make some decision about the null, which is height is not correlated with speed, and make some decision about how that correlation exists. So work on that for a few minutes. I'm going to mute myself. I want to finish working on correlation around 11:30 and then move on to paired sample t-tests. So work on this for about 10 to 12 minutes, and then I'll come back and review it, and then we'll move on to paired samples t-tests. So give this a fair stab, and then we'll work on it. We'll review it in a few. And if you have questions, do leave them in the chat. I mean, I can't come around to your group or listen to what you're saying and jump in and say, that's not the right way to do it. But if you have a question, please do bring it up. Okay, so how about 2 more minutes? So 11:25, and then we'll go through this one, and then we'll use this to go right into paired samples t-test, which really is just like a regular sample t-test, except it uses correlation. So 2 more minutes to work on this, then I'll spend 5 minutes reviewing it, and then we'll move on. Okay, so if you haven't finished, that's okay. You have all of the rest of the snow day to finish and to keep working on correlation. But let's review. Whoops, there goes my thing. Here we go. Okay. So I'll erase those for now too. If I was really good, I would know how to like select and move stuff. Nope, doesn't do it. Ooh, let's try this. There we go. That's primo stuff right there. Okay. Okay, so it's fancy. We know that z equals the sum. Not z. This is r. R equals the sum of zx times zy divided by the number of pairs. So the first thing we have to do, we have to multiply zx and zy, right? So here, we have to multiply this. So it doesn't matter which one you call x and which one you call y, as long as you're consistent throughout the whole question. So let's call height zx and speed zy. So what we have to do is multiply this by this. So this will be our new column. And this we get negative 2.56. Right? You multiply a positive by a negative, you get a negative. You multiply two negatives, you get a positive. You multiply two positives, you get a positive. Okay. So we go along and we multiply our two z's together. So this is what you should have gotten. This is just straight multiplying. Multiply anything by 0, it's 0. That's easy. Okay, so these are the multiplication of all your zx's by your zy's. So first thing you do is you have 8 pairs. You do 8 multiplication. You don't add them up first and then multiply or something weird. You do, for each pair, you multiply them together. Now we sum. So now we find the sum, which is, remember, is this little sign here. That's that guy. And that equals negative 6.82. Okay, so now we've done all of this. So this negative 6.82 is the whole top of this equation. So we have negative 6.882 divided by the number of pairs. So we go, this is a pair, this is a pair, this is a pair, this is a pair, that's a pair, that's a pair, that's a pair, that's a pair. 8 pairs. So negative 6.82 divided by 8 gives us an R of negative 0.85. And the sign is important. So don't just drop the negative. A negative correlation is a negative correlation. So if it's a negative 0.85, it's a negative 0.85. Okay, so negative 0.85. Well, that's fine, but now what do? Right? You have to compare that to some critical value of R to see if that correlation is a statistically significant correlation. So you find degrees of freedom. Now I can erase this raw data. So now this hypothesis testing is the same as you've done. You calculate your test statistic, then you have to find degrees of freedom. In this case, it's number of pairs minus 2, so it's 8 minus 2, which is 6. You go to the back of your book, you go to the R table, the critical value for R table, and at 6 degrees of freedom and alpha of 0.05, since the question didn't specify anything different, you can assume alpha of 0.05, you find a critical value of R, so R crit, at 6 degrees of freedom is 0.707. And remember, the critical value is on both sides of the distribution, right? So it's 0.707, and it's also negative 0.707. And what you're looking for is a statistic that is more extreme in magnitude, either positive or negative, than your critical value. So your value is negative 0.85. The critical value is 0.707, or remember, you're also reading this as negative 0.707. So your value, negative 0.85, is a more extreme value than negative 0.7. So here you would reject the null hypothesis, reject H naught. And, typically in recitation, right at this point, I would ask you, and what would be your kind of one-sentence lay summary? But since I don't have fast enough response to do that, because it's easy for everyone to be silent on the internet, I will tell you, is that height is probably correlated with speed. And then what you can say is taller kids tend to run faster, tend to be faster at this race, right? Because the kids who were tall had the lowest speed. So as height increases, speed decreases. That's that negative correlation. So just to draw it out graphically, just to make it more clear, what this data is showing us is we called height x, right? So just to keep it kosher with what we used zx, zy. So okay, what we have here is that this is like a tall person who has low speed or low. Yeah, I mean, it's called speed, but really it's measured in how fast they're finishing the race. So don't be confused by what these variables are called. Right, so your data looks something like this, where you have tall kids tend to be down here, short kids tend to be up here. Whoa, I do not want that. It looks something like this, right? So as height gets bigger, speed gets lower, right? And if you look at the raw data, you can see that. So with the first person, a height of 60 inches has a speed of 8. So that the height has a positive z of 1.57, and speed is a negative z of 1.63. And that goes similarly. People who have smaller z for height have a larger z for speed. that's showing that negative correlation. A positive correlation would be as one goes up, the other goes up. So if it was a positive correlation, not that it is, but if it was a positive correlation, as height went up, you would see speed go up. Again, calling this variable speed is not great. It's a little confusing. Really, it's time to finish race. So if it was positive correlation, you would see as height goes up, time to finish race would also go up. But that's not the case. We have a negative correlation. As one goes up, the other goes down. Okay, so if you have questions about that, please do put them in the chat, and we can go over that. But that's correlation. Correlation is looking at how two variables correlate in measures of their variance by standard deviation. Remember, z is a measure of variance. It's measuring how far away a given score is from the mean in units of standard deviation. So everything involved in correlation has to do with variance distances. I told you, remember the first class I said, variance is the most important thing in statistics. We're going to talk about all the... Are you there? Okay, stream resumed. I think I may have lost you there for a second, but it's going now. So, okay. Sorry about that. So again, if you want to do more correlation questions, go ahead and do number... Oops, I'm having a small technical issue. There we go. Go ahead and do number 6 from that same chapter. So either page 324 in the old book or page 296 in the new book. So work on that, and we can go over that next week in class, or I think Dr. Kiliansky put the answer to those up on Sakai, so either of those. But this is another good question to work on, so please do that. Okay. So if there's no other questions about correlation, please do put them in the chat, and if there's not, then we can move on. Okay. So, moving on. The whirlwind of statistics. Let's talk about paired samples t-tests. So previously, for exam 1, so set the way back machine for 3 weeks from now, or 3 weeks before now, we did independent samples t-test. Probably spelling this wrong, but that's okay. Independent samples t-tests. Right? And what I had said in class was the independent samples part means that your two groups, like class A and class B, no one in either of those groups is also in the other. So like no one in class A is also in class B. The individuals that make up those two groups are completely independent from one another. There's no overlap between the individuals in those two groups, right? So like if I'm comparing section 1 and section 2 of my recitations, I can't have anyone be in both. They have to be completely unique groups. That's independent samples, right? The people are independent. Paired samples says that's not true. Paired samples says that the people that are in group A are the same people that are in group B. So a lot of the time you see this with longitudinal tests, tests that are done over time on the same group. So for example, you want to see if Advil or Tylenol has a headache reducing effect. So one way you could test this is get two independent groups of people who have headaches. You give one group Advil or Tylenol. You give the other group placebo, or sugar pill, nothing, no active drug. And then you give them that, and then you ask them if they have a headache or not. Another way you could do that is take one group of headache users, first ask them if they have a headache or not, if they have a headache, how their headache pain is, then give them drug, and then wait and ask them a second time their headache pain. So that type of doing one group being measured twice is an example of a paired samples t-test. Having two independent groups being measured once, so only having one measure of headache pain with two independent groups, is an independent samples t-test. A paired samples t-test is having one group of individuals being measured twice with some intervention in the middle, with some independent variable used in the middle, some experimental manipulation in between the two measurements. So that's a type of paired samples t-test. It's not the only type. Let's say there are siblings, or there are other people who you would think would be some way non-independent, right? Let's say we're measuring the grades of students in my sections versus the grades of students in some other TA sections. Well, sections 1 and 2 are not completely independent, right? There might be some correlation between sections 1 and 2 because I teach both of them. So they're not completely independent. There is some dependency between those two groups. So most often you'll see it as some sort of longitudinal test, but just to put it on your radar, it's not the only way you'll see a paired samples t-test. It's not exclusive to longitudinal, but it's often longitudinal. Okay, so the big difference, remember that a t-test is calculated as follows. T equals the mean of group 1 minus the mean of group 2 divided by the standard error, the estimated standard error of difference. Right? Now that equation will remain the same. The estimated standard error of difference is calculated as follows. It's the square root of SEM of the standard error of the mean for group 1 squared plus the standard error of the mean. Again, these are both estimated, being lazy. Standard error of the mean for group 2 squared. You remember that, right? And then to calculate the estimated standard error of the mean, it's the standard deviation for your sample divided by the square root of the sample n minus 1. That's all review, right? That's all independent samples t-test. So all this is independent samples t-test. Now the only thing that's different in a paired samples t-test is how you calculate the estimated standard error of difference. What happens is you add something to it, or subtract, I guess is the more fun way of saying it. So what you do is, that should be an S. So what you do is you just change the equation for the estimated standard error of difference a little bit. So it's still the estimated standard error of difference for group 1 squared plus the estimated standard error of difference for group 2, the estimated standard error of the mean for group 2 squared, and then you subtract 2 times the correlation times standard error of the mean 1 times standard error of the mean 2. So this part is new. Everything else is the exact same. The only difference now is that your two groups are correlated with each other. So we just talked about correlation and how you can see if things are correlated. Now you have two groups that are correlated. Usually it's because it's the same people and they're correlated with each other, right? If I experience very strong headache pain at time point 1, even if I take Advil and I get a reduction in headache pain, I may still experience high headache pain compared to everyone else, right? If we all go down in headache pain, but I'm just someone who's very sensitive to that, I'm still going to be a high pain feeler even when all of our pain has reduced, because I'm more like myself than anyone else. So if I'm just a person who experiences that pain, even if I reduce my pain, I may still have higher pain than everyone else. We're correlated with ourselves, right? So the difference is that you're adding in the correlation. You're adding in a Pearson's R, which is right there, this guy. So this whole piece is new, but the new piece is you're adding in the correlation. Okay, so I'm going to have to erase this because there's not enough space to have it all in one place. But I'll give you a question, I'll give you some raw data to practice this. It's just like a regular paired samples, independent samples t-test, except you're adding in a little bit of extra stuff when you calculate the estimated standard error of the difference. Okay, so this is chapter 15 in the old book, 13 in the new book, and that's page 473. Whoops, I really am having problems writing today. Page 473 or page 450. We'll do question 1. And I'll give you some data here. So we have pre-practice and we have post-practice. So here you can see we have one group with 2 time points, and practice is going to happen in between the 2 time points. That's the experimental condition. So for pre-practice, we have a mean of 12.25 and a standard deviation of 3.15. For post-practice, we have a mean of 10.25 and a standard deviation of 2.73. And the important thing is the correlation between pre and post, the R value for that is 0.79. And it looks like, I don't have the book open, but it looks like the N for each group is, I'll have to look it up. Let me pull out my book. Go to page 473 and I'll tell you. Right. Our N here is 8. Right, so N equals 8. Okay, so I keep making this stupid line. To work on this one, so I'll give you some equations, right? T equals M1 minus M2 divided by the estimated standard error of difference. The estimated standard error of difference oh, it's like mirroring. That's really strange. Okay. Is that Degrees of freedom for paired samples t-test is n minus 1, because you only have one group, so there's only n minus 1. One group of individuals, I mean. And I think that's all you need, right? Then I guess you need the standard error of the mean. Okay, so work on this one, and then we'll go over it. I apologize for like cramming things onto here, but we do the best we can. Whoops, I'm starting a free trial. Don't want to do that. Okay, so work on that for a few minutes. If you have questions, please do bring them up. That should be everything you need. Remember, what you're doing is you're calculating a test statistic. In this case, it's t. You then have to find Alex Love. That is a great question. It depends. So he could give you the R, or he could give you the data that was just given to you previously. Like he could give you Z values and first ask you to calculate R and then calculate T. That's definitely a possibility. In that case, it's like you're testing both correlation and paired samples t-test in one. So the answer is it depends. It could be either. And in that case, you'd be given like all the Z scores to do an R, Pearson's R. And then you'd have to do that first, and then you'd have to do a paired samples t-test. Now, an important thing to bring up, this brings up an important aspect. If the Pearson's R is not statistically significant, you would not use it in a paired samples t-test. So you would have to calculate R, you would have to find your degrees of freedom, find the critical value for R, calculate, you would then calculate or fail to reject or reject the null. If you fail to reject the null hypothesis, you would then just do a regular independent samples t-test. So you wouldn't be able to, like, using a non-significant R in a paired samples t-test doesn't make sense because you're saying, I don't have enough evidence to say there's a relationship between these two groups. So that R, that non-statistically significant R, is uninterpretable. So you can only use a statistically significant R when you are calculating paired samples T. And if it's given to you, you can assume that it's statistically significant. Linda asks, is there a different equation for degrees of freedom? So in an independent samples t-test, since you have two groups of individuals, its degrees of freedom is n minus 2. In a paired samples t-test, since you only have one group of individuals, like the number of people is just one group of people, it's n minus 1. So it's not very different, but it's that. It's n minus 1 in this case. Okay, never mind. No problem. So work on this for a few minutes. I'll give you maybe until 5 after 12, just because I rambled for a little bit. So work on this, and then I'll go over it. So I'll mute myself. I need to go get some water, and then I'll be back. Please do keep asking questions. Hey, so Jenna asks, what do you use to find the critical value? You use the same critical t table that you normally use. So the critical value, the table for critical t. It's where's my book? I can find it. So it's table C. So remember, you always want to use the two-tailed critical value test, or find the critical value for the two-tailed test. And in that case, it's table C. Okay, so keep working on this for a couple more minutes, and then I'll review it. And I'll also give you some more to work on for the rest of the snow day. Mel, yes. So if the question doesn't say, you can assume an alpha of 0.05. So for this question, use alpha of 0.05. Okay, so if you haven't finished, that's okay. I'm going to review this one, and I'll give you another question to work on afterwards. So I'll try to select and move the given data, give us more space. Okay. Okay, so we know that t equals m1 minus m2 divided by the estimated standard error of difference. And we have m1 and m2, right? So the whole problem is calculating the estimated standard error of difference. And the first thing we need for that are the estimated standard errors of the mean. So estimated standard error of the mean for group 1 equals 3.15 divided by the square root of n minus 1, so 8 minus 1, or 7. And that equals 1.19. And then the estimated standard error of the mean for group 2 equals 2.73 divided by square root of 7. And that equals 1.03. Okay, so those are our estimated standard errors of the mean. So now we have to square those, right? Because we ultimately want to get this minus 2R SEM1 SEM2. Right? This is ultimately what we want. So we square this, and we square this, and that equals 1.42, and that equals 1.06. Okay, so now we have everything we need. So now we can calculate the estimated standard error of difference. So estimated standard error of difference equals the square root. I'll make another color so we don't lose ourselves. 1.42 plus 1.06 minus 2 times 0.79, that's R, times 1.19 times 1.03. Right, because remember, that second half of the equation is just using the regular standard error of the mean for groups 1 and 2, not the squared standard error of the mean. So the first part is the estimated standard error of the mean for group 1 squared plus the estimated standard error of the mean for group 2 squared minus 2 times R times the regular estimated standard error of the mean for group 1 times the regular estimated standard error of the mean for group 2. So if you calculate all of that out, so this whole part, this equals 1.94. That's this part. Whoops, I keep doing that. So this is this, right? And when you calculate all that out, you get an estimated standard error of difference. Don't forget, at the very end, you have to take the square root of, well, that gives you square root of 0.54. So this plus this minus that equals 0.54. The estimated standard error of difference, therefore, is the square root of 0.454. And then, if you take a little more space, and do 12.25 minus 10.25 divided by, let me just calculate the square root of 0.54 really quickly. If my fingerprint works, there it goes. 0.54 square root equals 0.73. 0.73. And that gives you a t. All right, so this is your t equation. T equals 2.74. So that's your paired samples t, 2.74. Remember here, degrees of freedom is m minus 1, so that just equals 8 minus 1 equals 7. Since it's not stated in the question, you assume an alpha of 0.05. Okay, and then from there, you find your critical value of t, which in this case, so t crit equals 2.365. Your value is greater than the critical value, right? It's a higher magnitude than the critical value. So in this case, you would reject the null hypothesis, H naught, and conclude that the post-test scores are smaller than the pre-test scores, right? Because the post-test scores are 10.25, whereas the pre-test is 12.25. So what you're saying is there is a significant difference between pre-practice and post-practice. Post-practice means are lower. Fatigue is the more likely prospect, right? Because then the question asks, like, is it fatigue or are they getting better or something? So in this case, you would want to conclude that fatigue is most likely it. And then you'd want to calculate effect size because you rejected the null. And so in this case, effect size is Cohen's d equals t over square root of number of pairs. So it's your calculated t, 2.74, divided by square root of 8, gives you a d of 0.97. And that would be how you do this question. So, and this recording is going to be available. So if you didn't quite get it on the first shot, you can kind of walk through the steps as I go and review it and hopefully find where you may have made a mistake. If you want more questions to work on, I would recommend in the same chapter, on the same page, do number 6. And we can review that in class next week. If you do number 6, that would be good. Okay, any other questions about paired samples t-test? Because I want to move on to ANOVA. Okay, so I know we're running a little bit behind what I wanted to have as our schedule, but let's do ANOVA because it's important. And we'll talk about ANOVA again next week too. So analysis of variance. Now, up until now, we've been comparing at most 2 groups, right? We've been doing either independent samples with a t-test, paired samples with a paired samples t-test. We've been comparing one sample to a population, like in a z-test, or a single sample t-test. But what if you have more than 2 groups? What if you wanted to compare multiple groups against each other? That's when an ANOVA comes in. So an ANOVA is kind of a special scenario of a t-test in which you have more than 2 groups. Again, analysis of variance. Variance is like the big thing in ANOVA. It's comparing one type of variance to another type of variance. Things that we call, you'll see, F is your test statistic, and that is calculated as the mean square between divided by the mean square within. The mean square between is calculated as the sum of squares between divided by degrees of freedom between. No. Yes, that's right. And then the mean square within is calculated by the sum of squares within divided by degrees of freedom within. Now you might be saying, these are all new words. What the hell does any of this mean? Have no fear. Because really, sum of squares is, so sum of squares, which is what we call SS, is really just another kind of measurement of variance. It's measuring variance. Remember, in a standard deviation, if you look at the equation for the standard deviation, it's, oh God, I have to do it from the inside out. It's x minus m, the sum of this, or x minus m squared, sum of squares, oh, see what I'm doing there? Divided by n, and take the square root. So here, even in the standard deviation equation, you're calculating a sum of squares, right? And then you're doing other things to it, but don't be alarmed by this suddenly new term. It's really something that you've been dealing with before in a slightly different way. So sum of squares is another type of measurement of variance, much like standard deviation, much like estimated standard error of the mean, estimated standard error of difference, sum of squares, another way of measuring variance. So what you're doing here is you're calculating the mean square between, which is a measurement of variance divided by degrees of freedom, which is a proxy of sample size, in this case, you can think of. So what this also gives you is mean square between, which is some measure of variance, and mean square within is another measure of variance. So you can think of this as variance within and variance between, and you're dividing them. And what you want, or what is statistically significant, is, so what is statistically significant? Big F. So the bigger the F, the more likely you'll have a statistically significant difference between groups. And what that means is if the mean square between is much, much, much bigger than the mean square within, you'll find difference. Right? Because look at the equation. If this is 100 and this is 1, then you get an f of 100, right? If this is 0.5 and this is 10, then you get an f of something very small. So I can't do that in my head. Okay. 0.5? 0.05. Duh. 0.05. Oh, man. Okay, so that's a nova. And, I mean, there's way more to it than that, but that's what we'll start with for now since we're running out of time. And we'll have more talk about ANOVA next week. I think it'll be much more comforting to teach this in person because it is kind of a whole world of statistics is ANOVA. So, consider this just dipping a toe in the very deep water of ANOVA, and take my word on it that we'll be spending lots of time on the concepts of ANOVA, both conceptually and computationally, next week in person in Recitation. Okay, so just to start getting a feel of ANOVA, here's what we're going to do. We're going to do, so this is, I need to make more space. And I'll give you the relevant equations again. So, chapter 12, old. Chapter 10, new. Page 369, old. Page 342, new. Let's do number 1. And there's given data for this as well. I give you the sum of squares between equals 74.4. And now there's a lot of things to think about conceptually in ANOVA, things that are worth spending time on next week in Recitation. I don't want to go over the time today because I have other meetings with students, so I want to make sure that those are good too. But it's like what is between, what is within. These are things that we're going to spend time talking about next week in Recitation in person. I have lots of graphs that you'll eventually get sick of seeing between now and the final, which is a lot more of the semester, that kind of go in depth on kind of what we're looking at. So take my word on it. If you're feeling, a little bit out of your depth, that's okay. Let's kind of get into the muscle memory first, and then we'll spend a lot of time on it next week in person, where I think it'll feel more natural kind of learning it. Okay, so degrees of freedom between is k minus 1, where k is groups, and degrees of freedom within is big N minus K, where big N equals total number of people. And then I also have to give you the means for each group. So mean of group A equals 4.2. The mean of group B equals 6.4. The mean of group C equals 7.2. And the mean for group D equals 9.6. So here I want you to practice calculating F. So this is mean square between divided by mean square within, where mean square between is sum of squares between divided by degrees of freedom between, and mean square within is sum of squares within divided by degrees of freedom within. So work on calculating F here. It's a brand new vocabulary, so we won't go totally in depth, like I said. Next week, we're going to go crazy in depth, but I want you to start here in calculating F, and then finding the critical value for F, which requires both degrees of freedom between and degrees of freedom within, and then either accept or reject or fail to reject the null hypothesis. So work on that for a few minutes. Ask questions if you have them, and then I'll unmute myself and we'll review it. Maybe we'll go 5 minutes over to like 12:35, and then we'll call it a day, and then I will see you next week. So work on that for a few minutes, and then I will come back to review. And now you can see my cat right there jumping in to also do ANOVAs with you guys, because he does enjoy ANOVAs. So take a few minutes to work on that. Oh, I should also give you the number of people per group. It's 5. So I'll write that down. Whoops. Right. So little n equals 5 per group. Okay, so let's go over. Let's go over this. So change colors. Okay, so we have first we need mean square between. So that's going to equal 74.4 divided by degrees of freedom between, which is k minus 1. So here we have 4 groups, right? 1, 2, 3, 4. So this is 4 minus 1, so it's 3. And that gives us an answer of, I didn't divide it yet. Hold on. 74.4 divided by 3. Whoops. 74.4 divided by 3. 24.8. Okay. And then our mean square within equals our sum of squares within, which is 16, divided by big N minus 1. So little n, which is the number of people per group, is 5. So I have 5, 10, 15, 20 people total, and 4 groups. So 20 minus 4 is 16. That gives me a mean square within of 1, which means f equals 24.8. Remember, it's mean square within, divided by mean square between, divided by mean square within. 24.8 divided by 1 equals 24.8. That's f. So now I have to go to the back of the book and find a critical value for f. So if we look in the book, which is here, now I'm looking for the f value. So that's table G, right? Critical values of f for the analysis of variance. And it asks for 2 degrees of freedom. The degrees of freedom for the numerator and the degrees of freedom for the denominator. So the degrees of freedom for the numerator is degrees of freedom for the mean square between, which is just degrees of freedom between, right? That's the numerator of the F-test. So that would be 3, right? Our degrees of freedom between was 3. So you go on top, you go to 3. And then degrees of freedom denominator is 16. So 3 to 16. And since it didn't say, we'll assume an alpha level of 0.05. And we get a critical value of 3.24. So crit f equals 3.24. Ours is 24.8. Our calculated value of f is of a larger magnitude than the critical value of f, so we would reject the null hypothesis. Remember, in ANOVA, the null hypothesis is that all the groups are the same. There's no difference between any of the groups. So what this is saying is there is some difference. Between groups. But at this point, you don't know where the difference exists. All you know is that there is some difference, right? So the final step is doing a Ttest test for honest significant difference, or Ttest HSD. Now I'm just going to walk through doing it once, and then you can practice later in the day, or we'll be doing it again next week for sure. So this is called, Ttest is the guy's name, like Tukey. Honest significant difference. And the way you calculate that is Where's my equation? There it is. So HSD equals a critical value of Tukey that you look up in the book at an alpha of 0.05 times the square root of your mean square within divided by little n, where little n is the number of individuals per group. So here, we go to table H to find the critical value, so that's this, and we would get a critical value of 3.95. So that's just looking it up in the book. So 3.95 times the square root of 1, which was our mean square within. Remember, it was 16 divided by 16. Divided by little n, which in this case was 5 per group. And this gives us an honest significant difference of 2.79. Now you're probably saying, what the hell does that mean? So, oh, I'm sorry, not 2.79. I was looking at the wrong thing. That gives us an honest significant difference of 1.81. But your question still stands. What the hell does that mean? So here we have our 4 groups, right? So mean of A is 4.2. Mean of B equals 6.4. Mean of C equals 7.2. And mean of D equals 9.6, right? These are the means for the 4 groups that we have, the average for each group. What Tukey's HSD is saying is if the difference between 2 groups is greater than 1.81 or negative 1.81, the magnitude is greater than 1.81, then we can say that those 2 groups are different from each other. The honest significant difference. So if the difference is greater than 1.81, we can say that those means are statistically significantly different from each other. So let's look. Mean 1 from mean 2. 6.4 minus 4.2 equals 2.2. 2.2 is greater than 1.81. So group A is different from group B. That also means it's different from group C and from group D, right? Because 7.2 and 9.6 are bigger than 6.4. Okay. Group B to group C. 7.2 minus 6.4 is 8 is 0.8, which means that those are not different, right? So B and C are not different from each other. Is B different from D? 9.6 minus 6.4 equals 0.2, 3.2. That's bigger than 1.81, so B is different from D. And then we want to check C and D. 9.6 minus 7.2, and that equals 7, that equals 2.4. 2.4 is bigger than 1.81, so C is different from D. So all the groups are different from each other except for B and C, is what you would, that's how you would say it. So first you find significant F. There is a difference between groups. Okay, well, where does the difference exist? Well, the difference exists between the groups. They're all different from each other except B and C. Or there's not enough data to determine if group B is different from group C. But we know it's different from group D, and we know that group A is different from all of them. We know that group C is different from group D. So that's how we know. So you didn't do this, so just watch along. But I will give you another question to do that you can practice as you watch the foot of snow fall. It hasn't really stuck to the roads yet. Everyone keeps saying it's coming, but we'll see. It won't be the first time that Rutgers closed for non-significant amount of snow. And I mean significant in the real sense and not in the statistical sense. Okay, so Uh, on this, you can still work on number 4. Remember, this is page 369 for the old book, or 342 for the new book. So work on that. The solutions were posted by Dr. Kiliansky on Sakai, but please don't look at them until you've actually given them a fair shot. I will review them briefly at the beginning of next week, so that we're all on the same page. And then we'll go from there. So any final questions? So if you have questions, please email me. I should be on campus tomorrow and Friday. So if you're around midday, either of those days, we can try to meet. I can't guarantee that, though, because depending on the snow and how meetings are canceled or not, then we'll see. But I will see you for recitation next week. Good luck practicing these questions: correlation, paired samples, t-test, one-way ANOVA. Please do practice them before our next recitation so that we can hit the ground running doing factorial ANOVA. And then enjoy the rest of your snow day. Don't do stats, all of it. Go outside and build a snowman or do whatever you'd like. So have a great afternoon. Thank you for coming to this digital recitation. There was a lot of people here the whole time, so that's great. And I hope you have a great rest of the day. So see you later.